Hello and welcome back to Quantitative Reasoning Online. Today we'll be doing starting chat lesson plan 5, lesson 11. So let's get to lesson 11. Mathematical modeling part 4. Lesson 11 and preview 11A. Population growth, interactive tutorial, and Nelly, a lot of questions. So no further ado, let's go with the tutorial. So let's see, we have lots of horses in, I don't know, Montana, Wyoming, Nebraska, who knows? So let's see, our objective. Describe whether output values are increasing, decreasing, or staying about the same. Describe whether output values are changing at an increasing rate, decreasing rate, or at a constant rate. Okay, in other words, is M changing? Don't know. Define the term inflection point, concavity, and logistic curve, and examine a graph and identify the region of the curve over which it is increasing at an increasing rate or increasing at a decreasing rate. Yes, increasing at an increasing rate, that's basically this guy, or increasing at a decreasing rate, that's basically this guy. We're increasing, but the slope of the line is also increasing. Here we're still increasing, but now the slope is decreasing. So that's what I meant by increasing at a decreasing rate. Okay, next slide. In the next class, you will need to analyze, that means with Stephanie, analyze the relationship of input and output value by examining a table of values. Sketch a graph of bivariate data and determine whether relationships are increasing or decreasing. The tutorial for the preview of Lesson 11, Part A, workbook, population growth begins here. So let's see. Question 1, Part A. Select the answer that describes the data provided. In the table, as the input value increases, the output values are, okay, so let's see. As we go this way, basically X is going up, and as we go along here, looks like Y is also increasing. 55 is bigger than 50, 60 is bigger than 55, 65 is bigger than 60, and 70 is bigger than 75. So the answer must be A. A increasing. Now, let's just make it official here. We said it. So again, just look at the table and saw as X was increasing, as we went left to right in X, Y was also increasing. Select the answer that describes the data provided. As the input value increased, the output value, okay. So we are increasing here, again. X is increasing. 55 is plus 5, 55 to 60 is a plus 5, 60 to 65 is 5 more, 65 to 70 is 5 more. So as X is going up by a uniform or constant amount, so is Y. So as X increases by 1, Y increases by 5. So let's look at A. Changes by larger and larger amounts each time. Nope. Changes by smaller and smaller amounts each time. Well, not getting smaller. changes by the same amount each time are not changing at all. Okay. So as x changes by 1, y is changing constantly by the same number 5. Outputs are increasing by 5 each time, so they are changing at a constant rate. C. That also means if it is at a constant rate, that means the slope, which is how y changes with respect to x, is a constant. So that means this would be a linear line. I suppose we could have gone the back one and got the equation of the line. Okay, select the answer that best describes the data. Okay, always going up by a constant amount here. Here we go plus 5, 5.5. 5.55, 5.555, I believe. All right. So let's see. In the table, as the input value increases, the output values are okay. Well, they're not staying constant. They're not getting smaller. So again, increasing. But notice it's increasing, but not at a uniform rate, though, or constant rate, or constant change. Every time. Let's see, as the input value increases, the output value changed by larger and larger amounts each time, possibly. Changed by smaller amounts, the same amount not changing at all. Yep, has to be A again. It's getting larger, and each one is successively larger. Yep. So A. Ooh, they would do that. View the median and select the correct answer. Select the answer, describes data provided in the table as the input value increases, the output value goes up. No change, no change, no change, no change. It means constant. So that means this guy will look something like that. Horizontal layout. Okay, again, same thing, no changes. Select the answer that describes the data value. As the input value increases, the output value changed by a large amount, changed by smaller, changed by the same amount, are not changing at all. I almost like to ask the same question again. That's okay. But technically, is 0 a change? Changed by the same amount each time? Yeah, definitely what we picked. Okay, let's see. This goes up by 1, minus 3, minus 3, minus 3, minus 3. So as x is increasing, y is decreasing by a constant amount. Yeah, so as x increases, y increases, x increases, y decreases. As x increases, y same. And looking at that, it looks like we have this guy. In each case, we are subtracting 3. Okay, that stays the same. So select the answer best described. As input value increases, okay, as input goes up, the output value changed by larger and larger amounts? No. Changed by smaller and smaller amount? No. Changed by the same amount each time? This one would have been like a minus 3, minus 2.5, minus 2.0, minus 1.5 type deal. We don't have. This is actually what we want. Changes by the same amount each time, going down and not changing at all. So let's see what we got here. Plus 1. Okay, we're increasing in y constantly. And let's keep big picture thought here. So select the answer in the table as the input value increases. All right, x is increasing. The output values are, okay, 135 is bigger than 50, 369 is bigger than 135, 1000 is bigger than 369, 2700, it is increasing. Yep. Whew. So we got here. From 1 to 2 was an increase of 85.9155. What's the other one going to be? Take a look. Need a calculator. So let's try 369.4602 minus 135.9155 for 233.5447, about 1004.307 minus 369.4602, 634.8468, and lastly 2730.017 minus 1004.307. 1725.71. Ooh, doggy. So change by larger and larger amounts each time. Yeah. Change by smaller. Same. Not changing at all. It's got to be this guy. Is there a pattern here? Times 3, times 3. Roughly by a factor of 3. Roughly. No, we don't want to do that. Yes, I do. Lost my light again. Light's back on. Let's see. plus 6, plus 6. Ooh, okay. Wow. Select the answer. Describes the data. The table, as x increases, the input, the output is increasing, not decreasing, and it's not meaning constant. Select the answer that describes the data. Again, as the input increases x, the output value changed by larger and larger. Okay, it's not getting bigger and bigger between steps. It's not increasing by a small amount. Changes by a small amount each time, not changing at all. This guy. Alright, so question 7. Do an inner search for the definition of words or word phrases given in part B through F. Look for sources with graphics that may help you understand more fully what the terms mean. Record the definition in your notebook using everyday words rather than very formal mathematical terms. You may wish to make a quick sketch to accompany the definition. So let's see. Let's see what part B term is. And part B, the word is concave up. So let's define concave up. So once you take a minute, I'm going to put me on pause and find what concave up means. So what'd you find? Let's see, concave up basically means you have a change of direction. So as a sketch, basically that would be a function that describes a concave up situation. Okay. Concave up is essentially, can be loosely defined as the slope of a tangent line. Okay, and here's a tangent line. So a tangent line I best describe this one without getting too technical. So a tangent line, as measured from left to right, RHHT, of course this is left to right. So a tangent line measured from left to right will transition from a negative slope to a zero slope and then to a positive slope. So here we have a negative slope, here we have a positive slope, and here we have a zero slope. I can also think of a concave up function where possess an absolute minimum value. So that's one way of defining concave up. There are other ways, but That's two of them. So part C, divine concave down. Well, basically just the opposite. Concave down and positive, slope 0, negative. Again, as you go left to right, so if the tangent line as measured from left to right will transition from a, and let's make that red, from a positive slope to 0 slope and then to a negative slope. Concave down function will possess an absolute, okay, maximum value as it changes direction. Which makes sense because at this point, where m equals 0 here, if I graph down xy, that's going to be the maximum value for it. So slope of tangent lines is measured from left to right will transition from a positive slope to a 0 slope and then to a negative slope. Concave down function will possess an absolute maximum value. Part D. Inflection point. Inflection point is point on a function, and I'm going to say line loosely, where the concavity of a function changes from up to down or down to up. For instance, here's one. Yeah, didn't change. So right here, it's basically a transition. At this point here, one could say, nuts. I could be going here, we're going there. Okay. So here I have up, and here I have down, and that inflection point is where it changes. So inflection point, point of a function where the concavity of a function changes from up to concave down, or down to up. Logistics curve. Okay. Why don't you put me on pause, and why don't you go research logistics curve. Logistic curve. Hopefully you took some time and looked it up. A logistic curve is a variation of an exponential. An exponential curve basically does that, while a logistic curve takes into consideration constraints. So a logistic curve may start off exponentially and then hit a maximum value. So logistic curve is S-shaped, and S-shaped curve is a exponential function that takes into consideration constraints on the system. People keep on saying, you know, there's a maximum sustainable population that the Earth can have. So let's look at us. Now, over the years, a long time ago, let's say, let's go with 1600. All right. Population was there, and over the years, as years progressed, you know, population increased slowly at first. Then somewhere along the line, it peaks. It gets to a maximum increasing rate. Then there's an inflection point, and it starts slowing down, and we get basically a max sustainable population. I mean, is that 7 billion, 8 billion, 9 billion, 10 billion? I don't know. Like I said, it's a max, but it looks something like that because, and of course, what happened in some regions, what causes this big increase? Let's see, probably the agriculture, the ag boom. We immensely increased the amount of production, farmland and cattle and everything else, and of course, which means more food, which means we can sustain a bigger population. But after a while, even with the more food, we get into a region where we just can't keep adding forever. We eventually do max out. So the logistic curve is an S-shaped curve. Yes, continue. It's an exponential function that takes consideration constraints on the system. Asymptote. An asymptote. Well, put me on pause. Look it up. What is an asymptote? Go look it up. So what'd you get? What I found was asymptote, a line where the function approaches but never touches. Okay. And during that one logistic curve that I drew just a little bit ago, there is a line. Man, those buttons. Basically, the limit. This guy will go out, keep going out further and further. He'll approach, but he'll never touch it. So we say we asymptotically approach a value. So a function, an asymptote, it's a line, it's a measure, it's a limit that the line can approach, but never quite get to. A line where the function approaches but never touches or crosses. Part G. Ooh, my. Here we have, and so let's see. So what was A? Okay. Sketch the graph on your paper, then place on the graph that illustrate each of the term you define, if present. Well, let's go with red. So somewhere about halfway is my inflection point. Something we're going to find out is, where does the inflection point of a logistic curve occur? It happens. Basically, half the limit. Halfway of what its potential maximum number is going to be. Okay. Which means this side of the curve is concave up. This side of the curve will be concave down. Alright? Concave up. Concave down. Inflection point. Here is an asymptote. This 100. And let's see, concave up, concave asymptote, and was E the inflection? Yeah. And this entire thing, the blue line that I've now turned mega red, that is your logistic curve. Okay. So when we're approaching, as we go left to right, as we approach the inflection point, the curve will be concave up. Going left to right, as we pass the inflection point, the shape of the curve will become a concave down, and it will increase over time, years, asymptotically to the limit, the population limit, the value limit. And here we go again. Consider the curve shown in the graph. Notice that the number of horses is increasing over time. Oh, number of horses, gotcha. Okay. Estimate the range in years when the number of wild horses is increasing by larger and larger amounts. The number of horses is increased by larger and larger amounts. Okay, that means larger and larger amounts means the slope is increasing. So I want to be when I'm concave up. Okay. And limit's 100, so 50. It's about 30 years. So I'm going to say from year 0 to 30. Because after that, like I said, it goes concave down, and I'm increasing still. So I'm still increasing, but at a less and less rate of increase. To about year 30. From year 0 to year 30. So this side of the inflection, I'm increasing, but I'm increasing faster and faster. This side of the inflection point, I'm still increasing, because as x goes this way, y is going up, but the rate of increase is going down though. Okay, estimate the range in years when the number of wild horses is increasing, but by smaller and smaller amounts. And I just did that. We'll be on this side of the curve. So from year 30 to about year 100. Okay. Now what causes this? Well, might have hit a population point where now the amount of food may be becoming a stressor. Maybe. So let's see, how confident are you that you can describe whether output values are increasing, decreasing, or constant? I'm extremely confident. Changing at an increasing rate, going up but not as fast, going up but not as, going up faster and faster, going up less, still going up but less fast, or a constant rate. Yes. Look at a logistic curve, see the inflection point in the concavity in everyday terms, increasing or decreasing. I'm pretty confident on that one too. Yeah. All right. Yeah. So let's see. We did that. Describe what output values are changing. We did that. Increasing or decreasing rate. Define the terms and examine the graph. We did all that. All right. So that makes us done with the population growth interactive tutorial. So you need to listen to me again or go back and just do it yourself and see if you can get the same answers, same results. Either way, I'll be talking to you shortly and we'll look at the questions 1 through 8. Till then, have a good day.